Welcome students. In addition to the thermodynamics and statistical mechanics lectures, I'm also simultaneously releasing some lectures in quantum mechanics, as that these lectures will be useful for the coming IIT JAM or GATE physics or CSR, JRF exams, right? So in quantum mechanics, I'll start with the series of lectures will be like this. The first topic will be photoelectric effect. The next one will be Compton effect. Next one is de Broglie's concept of matter waves, uncertainty principle, and then we'll enter into the Schrodinger wave equation, and its applications, mathematical formulation, and all. Now, at the end of each topic, I'll be solving some problems which have appeared in previous JAM papers or previous GATE papers, like photoelectric effect is there. After completing the theory, right, we'll solve some problems which have appeared in the previous JAM papers or GATE papers, like that. So please watch the video completely, right. These lectures will be slightly longer than my earlier lectures, they may be around 1 hour or more than 1 hour also, so such that I can complete one topic in one lecture, right. Now the first topic is photoelectric effect. Now photoelectric effect means this effect was discovered by a scientist called Hertz in 1889. What is this photoelectric effect? When light of suitable wavelength goes and falls on a photosensitive metal plate, electrons are found to come out. Photoelectric effect means the electrons are coming out because of the action of light. Hence the name photoelectric effect. Now I'll take some photosensitive metal plate like this and we'll send some light. Right, when this light goes and falls on this metal plate, electrons are found to come out of the surface of the metal. These ejected electrons which have come from the metal plate are called photoelectrons. And if you you put this photosensitive metal plate in an evacuated glass chamber, connect that plate to the negative terminal of a battery, put another metal plate here, connect it to the positive terminal of a battery through some ammeter. These electrons will get attracted towards this positive plate and start flowing in the circuit like this. When electrons are flowing like this, we say current due to them will be in opposite direction. Current will be in this direction like this. This current in the external circuit is called photoelectric current. These emitted electrons are called photoelectrons, and this effect is known as photoelectric effect. Now, what are the salient features which have been observed in this photoelectric effect means? The first one is the kinetic energy of photoelectrons is found to be independent of incident intensity. The kinetic energy of photoelectrons is found to be independent of the incident intensity of light, whereas photoelectric current depends on it. Means the kinetic energy of photoelectrons, the kinetic energy of photoelectrons is not depending on the incident intensity. In 1889 or up to 1900, right, light was thought to be a wave. That light is emitted, right, continuously from the source, and energy is continuous, and emission and absorption both are continuous. That is Huygens wave theory of light. According to wave theory, right, intensity means more energy. Now from the metal plate, now inside the metal, the situation will be like this. There will be large number of free electrons. Why metals are good conductors? Because they have large number of free electrons. How many free electrons will be there? Nearly 10 to the power 23 electrons will be there. Those free electrons are free to move anywhere within the solid, just like molecules of a gas in a container. They can move throughout the volume of the metal, right, freely, but they are not free to come out of the surface of the metal. They are not free to come out of the surface of the metal. Why means? Because of the presence of these positive charged ions in the crystal lattice, there comes one potential barrier on the surface of every metal. Right, these electrons can move freely throughout the volume of the metal, colliding with what you call positive ion cores, but they are not free to come out of the surface of the metal because they are not having sufficient energy to overcome that potential barrier and come out. Right, so they will be moving just like inside the metal surface, inside the metal volume, right, just like molecules of a gas in a container. Now they are able to come out of the metal means what? Somebody is giving that extra energy, right, such that they can overcome this potential barrier and come out. That energy is being given in the form of light here. According to classical wave theory of light, light of more intensity means more energy, means more energetic light comes and falls on the electrons. Electrons should come out with higher and higher kinetic energy. Means according to classical wave theory, as the intensity of the incident light increases, right, the kinetic energy of the photoelectrons should increase. But what has been observed is kinetic energy of photoelectrons is independent of the incident intensity, whereas Photoelectric current is depending. As you are increasing the intensity, current is increasing. Current is increasing. This aspect could not be explained by classical wave theory properly. Okay, why it is happening like that? There is no answer in classical wave theory. Next, we go to the second salient feature or important feature of what you call observed aspect of photoelectric effect is the kinetic energy of photoelectrons is proportional to the frequency of incident light. Means the kinetic energy of photoelectrons Ke is found to be proportional to the frequency. According to classical wave theory of light, intensity or energy of light is proportional to mu square, proportional to square of the amplitude. Okay, in wave motion, right, energy is intensity, means energy, right, proportional to square of the frequency. So as intensity is increasing, right, the kinetic energy of photoelectron should be proportional to square of the frequency, but not frequency. But what has been observed is kinetic energy of photoelectrons is directly proportional to these depending on the frequency of incident light, not on its square. Okay, why like this also could not be explained by classical wave theory. The third one, there exists a threshold frequency mu naught. Threshold means cutoff frequency, minimum frequency. Okay, right, cut-in frequency you can call. Right, there exists a threshold frequency mu naught below which photoelectric emission ceases. Means when you keep on decreasing the frequency of incident light, okay, below a specific frequency mu naught, right, not even a single photoelectron is coming out. Whether you send the light from a small bed lamp or from a big searchlight, okay, not even a single photoelectron is coming out if the frequency of incident light is less than a specific value mu naught. This mu naught depends on the type of the metal used. Okay, different metals have different mu naught values. Okay, next one. The fourth important aspect of photoelectric effect is there is no time loss in this process. Means the moment light falls, electrons are found to come out. Okay, according to classical wave theory, the transfer of energy from a wave to a material particle should be a lengthy process. Okay, means we expect if light is really a wave, okay, it takes a lot of time for the energy transfer. Electrons should come after say half an hour or 1 hour or something like that. Okay, but what has been observed practically is the moment light falls, electrons are coming out. Okay, why there is no time loss in the process also could not be explained by classical wave theory of light. Okay, like this, the four salient features of photoelectric effect could not be explained properly by classical wave theory of light. That is, light is emitted in the form of waves, which was a popular thought in those days. Okay, and this Huygens wave theory also is very successful in explaining all the properties of light. Light has how many properties? 6 properties light has. Light always travels in straight lines. Rectilinear propagation of light could be explained by what you call wave theory. Reflection of light, refraction of light, interference, diffraction, polarization. All the 6 properties of light could be perfectly explained by classical wave theory. Entire optics got developed on the basis of wave theory only. But such a highly successful wave theory of light, why is it failing to explain this photoelectric effect? Could not be understood easily. Okay, right. Before that also, there was some problem with the wave theory of light regarding black body radiation. The radiation coming out of a perfect black body, right, that radiation energy distribution curves could not be explained by classical theories. There were 2 formulae have come, Wien's black body formula and Rayleigh-Jean formula. Both the formulae could not explain, right, the classical, what you call the distribution of energy of black body radiation. Okay, radiation energy in black body, right. So at that time only, to explain that radiation distribution energy curve, Max Planck has come out with what is known as Max Planck's quantum theory. Okay, right, according to quantum theory, right, what Max Planck thought is, since light as a wave could not explain the black body radiation, if not a wave, what else light could be? Okay, wave means continuously light is getting emitted or absorbed. Okay, if it is not continuous, what should it be? It should be discrete and discontinuous. Okay, but Max Planck was extremely careful in not using the word particle. Why? Before Max Planck, before classical wave theory only, Newton came out with what is known as Carboscular Theory. Light is emitted in the form of tiny particles called corpuscles. Okay, shot into space in direction from the source that is emitting light. But Corpuscular theory of light failed. Okay, there were many drawbacks. To overcome those drawbacks only classical wave theory has come. Okay, Huygens wave theory has come and became successful. Now again saying that light is a particle means going back by 100 years or 150 years. Okay, already particle nature of light is failed once. Okay, so what Max Planck said is, he did not use the word particle. He said that let light be emitted light be emitted discretely and discontinuously in the form of tiny packets of energy, he said. He did not use the word particle. He did not use the word particle. He was extremely careful in that sense. Okay, he said that they are simply quanta. Quanta in Latin means packets. Quantum means a single packet. Okay, each quantum of light is having an energy h nu, he said. H is known as Planck's constant, one of the smallest constants. Okay, 6.626 into 10 to the power minus 34 joule seconds, and nu is the frequency of light. Okay, so he came out with what is known as quantum theory. Okay, light is not emitted continuously in the form of a wave, but it is emitted in the form of tiny packets of energy. The energy of each packet is equal to h nu, he said. With this concept of discrete and discontinuous energy values, he could successfully derive one formula also for that black body radiation energy distribution curve. Okay, and it had fitted perfectly with the experimental values. Okay, but still people were not ready to accept this quantum theory. Why? They were very happy with wave theory. Wave theory was extremely successful explaining all the properties of light. Moreover, Maxwell's electromagnetic theory is also based on wave aspect of light only. Now if suddenly some man comes and says that light is not a wave but it is a particle, means like going back to 100 years or 150 years, Newton's times only. So other physicists were not ready to accept Max Planck's quantum theory initially. Okay, because if they accept quantum theory, they have to rewrite the entire optics again. We have to explain interference, diffraction, polarization, and Maxwell's EM theory also in terms of photons or in terms of this quanta. Okay, that's a very big thing. So what they thought is, if not today, tomorrow or day after tomorrow, using wave theory only we'll explain black body radiation. But we don't use this quantum theory. Okay, they were of that opinion. So it was lying like that without any acceptance. Quantum theory was just lying like that. And again, after some years, right, Hertz discovered this photoelectric effect. Here also, right, the wave theory is found to fail. Okay, so in 1905, Einstein was the first scientist. Okay, Einstein was the first scientist to use this Max Planck's quantum theory. Okay, in 1905, Einstein used this Max Planck's quantum theory and could successfully explain all the four salient features of photoelectric effect. Okay, see, remember, Einstein got his Nobel Prize not for his theory of relativity. It is for this photoelectric effect explanation only. Means it is other than Max Planck, right? Who was the first scientist to use this quantum theory? Einstein. Later on, in 1905, this happened. Okay, means one success to quantum theory or one support to quantum theory. Later on in 1911, Niels Bohr, in those days he's a very big scientist. Okay, right? Niels Bohr has used the same quantum theory in his explanation of the spectrum of hydrogen atom, and he was successful there also. Means quantum theory has got second support. Okay, next in 1921, what you call in elastic scattering of light, right? Compton has used the same quantum theory, right? That man has went a step ahead of both Max Planck and Einstein. Okay, and said that let these particles, let these packets of energy be not called simply as packets, but let them be particles only, he said. He went a step ahead of Einstein and Max Planck also. He said that they are not simply packets, they are simply particles of energy. We can directly call them as particles, he said. And he has expressed them. Every particle should have two properties. Particle must have some mass. When it is moving, it should have some momentum also. So he has given the expression for mass of each light packet, and he has given the expression for momentum of each light packet. Moreover, he was the first scientist to use conservation of momentum principle to light. Okay, see, conservation of momentum principle we come across in mechanics. Okay, we don't study about conservation of momentum in optics. Okay, right? Optics is a wave phenomena. Momentum comes in mechanics. Okay, but Compton was the first scientist to apply conservation of momentum principles to it. Okay, then people, what you call, people realize the significance of quantum theory. They can no longer ignore this Max Planck's quantum theory because it is gaining more and more support from other aspects. Okay, it is becoming more and more successful in explaining many other aspects. Wherever classical theory is failing, quantum theory is becoming successful. Thus came what is known as dual nature. People were forced to accept what is known as dual nature of light. Okay, in around 1922, like that. Okay, from there onwards, immediately de Broglie has come, said that when you are accepting light to be a particle apart from wave, why not accept a metal particle like this pen or electron or proton to behave like a wave? Okay, and he came out with formula also. People were forced to accept that also because two experiments have confirmed beyond doubt that particles also behave like waves. Okay, so by 1922-23, entire physics got shattered for some time. Okay, so new ideas have come like this. That's why it is known as modern physics. Though no longer it is modern, it is 100 years old, still we call it as modern physics. Why? These ideas were new in those days. Okay, right? People which are things which were thought to be waves, they are not behaving like waves, they are behaving like particles, right? Things which are behaving like pure particles suddenly started behaving like waves also. Okay, that is the reason for the development of a new branch of physics called quantum mechanics. Okay, so quantum mechanics originated from that concept from 1923-24 onwards, right? The word mechanics of a wave or quantum mechanics has come. Okay, so the first step to for quantum mechanics is starting from Max Planck's black body radiation. The second effect is this photoelectric effect. Now, how Einstein could explain all the four salient features of photoelectric effect means it is like this. Okay, right? This is a photosensitive metal plate, right? Light is not in the form of waves but in the form of tiny packets of energy. Tiny packets of energy, or later on these packets were given the name called photon. Okay, photon is a quantum of light, photo. Okay, right? Each photon's energy E is equal to h nu. H is called Planck's constant, nu is the frequency of light. Now what happens here is, according to quantum theory, more intensity means more number of photons will come. Okay, energy of each photon depends only on frequency, that's all. Okay, now you take one bulb, sodium vapor lamp you take, use a 40 watt sodium lamp you take. Okay, you switch on, some intensity of light will come. Okay, how many photons are coming per second? Suppose say some 10 to the power 20 photons are coming. Okay, what is each photon's energy? Each photon's energy depends on the frequency of light coming out of sodium vapor lamp. Okay, sodium vapor lamp emission wavelength is h nu. Nu equal to c by lambda we can write. So what is the wavelength of the sodium lamp, light coming from sodium lamp? Around 5890 or 5896 angstroms. So unless you change that frequency, energy of each photon is not going to change. What is the meaning of doubling the intensity or tripling the intensity, right? You want to double the intensity means we will switch on another 40 watt lamp. When you switch on another 40 watt lamp, what will happen, right? The number of photons coming out will get doubled. Instead of 10 to the power 20, now 2 into 10 to the power 20 photons will come. Okay, but energy of each photon remains same because we are not changing the frequency of sodium lamp. Okay, right? Frequency of that light coming from sodium atoms. Okay, right? We are simply increasing the intensity. So according to quantum theory, energy of a photon depends on frequency. Without changing the frequency, you are increasing the intensity means simply you are increasing the number of photons, that's all. Energy of each photon remains same. Okay, now you take same this glass bulb and a metal plate is here like this. Okay, you are sending now light means in the form of photons you are sending. Okay, each photon's energy E is equal to h nu. Okay, say the energy of each photon, I will fix the frequency in such a way such that the energy of each photon is 5 electron volts. Okay, initially I am sending say 100 photons. I am giving a rough example. Okay, right now 100 photons each with 5 electron volts energy, they go and fall on this metal plate, and inside there are large number of free electrons. Okay, moving here and there freely. They are unable to come out of the surface of the metal because of that potential energy barrier. Now our photons are going and colliding with those electrons, and each photon gives rest its entire energy to our electron. Our electron acquires extra energy of 5 electron volts. Okay, now in order to come out of the surface of the metal, to overcome that potential barrier and come, right, each electron has to spend some minimum amount of energy, right? That say in rough example it is 1.9 electron volts. Say I'll call this as work function of the metal phi, photoelectric work function. What is photoelectric work function? Minimum energy required to remove the electron from the surface of the metal. Okay, every electron, in order to come out of that surface, it has to spend a minimum of 1.9 electron volts. Say this is known as work function. Now what will happen? Every electron is getting an additional energy of 5 electron volts. Out of 5 electron volts it spends 1.9, and electron comes out with remaining energy becomes the kinetic energy of the electron. So 5 minus 1.9, 5 minus 1.9 will become the kinetic energy of the electron, which is nothing but 3.1 electron volts. So every electron comes out with 3.1 electron volts like this. Okay, right? This is how photoelectric effect happens. Now what is the first observed feature? Kinetic energy of photoelectrons is independent of incident intensity. Now, I want to double this intensity. Doubling the intensity means what? Simply instead of 100 photons, now I will send 200 photons. but each photon's energy remains as 5 electrons only, right? 5 electron volts only, because I have not touched the frequency. Simply I have increased the intensity from 100 photons to 200 photons. What will happen now? 200 photons go and fall on the metal plate. 200 electrons acquire that 5 electron volts. Every electron spends about 1 electron volts. And how many electrons will come out? 200 electrons will come. Okay, but each electron's energy still remains 3.1 only. That's why kinetic energy of the photoelectron is independent of the incident intensity. But photoelectric current depends on it. Why? Instead of 100 electrons, if 200 electrons are coming out, 200 electrons flow in the external wire, right? Current is nothing but charge per unit time. More electrons, more charge, more will be the current. Means when you are increasing the intensity, kinetic energy of photoelectrons will not change. It will remain as 3.1 electron volts only. But more and more electrons will keep on coming out. Photoelectric current keeps on increasing. Okay, the first salient feature which could not be explained by classical wave theory could be easily explained by this quantum theory. Okay, by Einstein using this quantum theory. Second one, right, kinetic energy is proportional to frequency of incident light. According to classical wave theory, it should be proportional to nu square, but it is depending on frequency only. Okay, how is that explained? Means now instead of 5 electron volts, if I send photons with energy 6 electron volts, okay, what will happen? 100 photons only, right? With 6 electron volts energy, they go and fall on the metal plate, right? 100 electrons will come out with what? 6 minus, they spend, each electron spends 1.9, 6 minus 1.9, right? Every electron comes out with 4.1 electron volts of energy. Okay, right? Now, what happened to kinetic energy? Kinetic energy of photoelectrons has increased from 3.1 to 4.1. This time, I will send photons with 7 electron volts energy. Okay, so when 7 electron volts energy photons go and 100 photons only, go and fall on the metal plate, every electron spends 1.9 and comes out with 7 minus 1.9, 5.1 electron volts of energy. Means what is happening? Kinetic energy of photoelectrons is increasing. How am I able to increase the kinetic energy of photoelectrons? By increasing the energy of the incident photon. How to increase the energy of the incident photon? E is equal to h nu. If I want to increase the energy of each photon from 5 to 6 to 7 means I should increase the frequency. So as I am increasing the frequency, energy of each photon is increasing, kinetic energy of photoelectrons is also increasing. Therefore, kinetic energy of photoelectrons, right, it depends on the frequency of incident light as observed. This could also be understood very easily using quantum theory. Okay, next one. The third point was, there exists a threshold frequency mu naught below which photoelectric emission ceases. Ceases means gets stopped. Okay, right. Now how to understand this means, now instead of 5 electron volts photons, now what do? I decrease the frequency. So energy of each photon decreases. So I'll decrease the frequency to such a value such that every electron now gets, every photon's energy is just 3 electron volts. Okay, instead of 5 electron volts photons, I'll decrease the frequency of the incident light. Now only 3 electron volts photons go and fall on the metal plate. Okay, right? Now what will happen? Out of 3, they spend 1.9 and come out with 1.1 electron volts of energy. Okay, still decrease the frequency of incident light such that now each photon's energy is just 2 electron volts. 2 electron volts photons go and fall on the metal plate. Out of 2 electron volts, they spend, every electron spends about 1.9 electron volts and comes out with 0.1 electron volts energy only. Now you still decrease the frequency to a specific value mu naught such that it corresponds to exactly this 1.9 electron volts of energy. Okay, that is, right, when frequency is mu naught, right, corresponding energy will be h nu naught. That energy will be exactly equal to 5, that is equal to 1.9 electron volts say. Okay, when the frequency of incident light is mu naught, the corresponding energy will be just 1.9 electron volts say. Now when 1.9 electron volts photons go and fall on the metal plate, every electron gets 1.9 electron volts, right? Every electron spends that entire 1.9, right, in order to overcome that potential barrier, comes out with 0 kinetic energy. Okay, it is not left out with any kinetic energy now. It has spent all its energy, right, in just coming out only. It comes out with 0 kinetic energy. Now what happens? You still decrease the frequency below nu naught, means you make nu less than nu naught. When you decrease the frequency below nu naught, right, photons energy will go below 1.9 electron volts. So you are sending 100 photons, each with energy say 1.8 electron volts. Okay, when 1.8 electron volts photons go and fall on the metal plate, they collide with 100 electrons. Okay, all 100 electrons will just get 1.8 electron volts energy only, but it's not sufficient to overcome the potential barrier and come out. So not even a single electron can come out. Okay, whether you send 100 photons or 500 photons or even 1 lakh photons also, means you send light from a small bed lamp or from a big searchlight also, if the frequency of incident light is less than the specific value nu naught, right, the 4 electrons will not get sufficient energy to overcome the barrier and come out, such that they cannot come out. Okay, so the existence of this threshold frequency nu naught, right, could also be understood very easily using quantum theory. Okay, and that nu naught depends on, varies from metal to metal. Different metals have different work functions, so corresponding to that, different frequencies, threshold frequencies will be there. Okay, so third aspect of photoelectric effect also could be explained perfectly using quantum theory. The fourth one is there is no time loss in the process. There is no time loss in the process means the situation is like this. Okay, consider a cricket ball, okay, at rest on some table. Okay, what is its kinetic energy? Since it is not moving, its kinetic energy is 0. Now what do? I'll take another cricket ball and what you call throw it with some velocity v towards our first ball. Okay, this is our second ball, say this is our first ball. Okay, I'll throw this first ball towards the second ball with some velocity v. It is having mass m, means it will have some momentum, it will have some kinetic energy k also. What will happen when this ball goes and hits that ball? The second ball starts moving immediately. Okay, earlier its kinetic energy is 0. Now it moving means it will have kinetic energy. Where from it got its kinetic energy? From the first ball. The moment this first ball goes and hits the second ball, transfer of energy takes place and second ball starts moving. Okay, there won't be any time delay in this process. It never happens that this ball goes and hits that ball and after 15 minutes or 20 minutes the second ball slowly starts moving. It never happens, isn't it? The moment this ball goes and hits that ball, the second ball starts moving. This second ball is nothing but our electron. The first ball is nothing but our photon with energy E equal to hν. Okay, that's why in photoelectric effect, the moment this photon goes and hits the second ball, right, the electron is moving. There is no time loss in the process, need not be any time loss also. Okay, because here it is not an interaction between a wave and a particle, it is interaction between two particles only. Okay, right, particle aspect of light, particle nature of light is becoming prominent in this case. Okay, so this is how what you call the fourth aspect of photoelectric effect also could be explained by Einstein perfectly. Okay, so after explaining all this, he has given one equation. Now what is the kinetic energy of the emitted photoelectrons means? I told you in my earlier example it is 3.1. How did I get this 3.1? 5 minus 1.9. I said what is this 5? Energy of E incident photon is hν minus what is this 1.9? Minimum energy required to remove the electron from the surface of the metal. It is called work function phi. This gives us kinetic energy. But write one subscript here. It should be K maximum. Okay, this is called the famous Einstein's photoelectric equation. K maximum equal to hν minus phi. K maximum is equal to hν minus phi. Right? This is how we write. K maximum or half m V maximum square is equal to hν minus phi, right? This is Einstein's photoelectric equation, which is nothing but a consequence of conservation of energy principle. Now why should I put a subscript maximum here? Means the emitted electrons will not have the same, all emitted photoelectrons will not have same kinetic energy. Okay, why means you take a metal, okay, inside metal suppose there are 1000 electrons. All are free electrons only, but all free electrons inside a metal will not exactly have the same amount of energy. Okay, we can visualize metal as a potential well. Inside a well, suppose there are electrons like this. Some electrons are having less energy, some electrons are having more energy like this. Okay, in order to come out of that well, so minimum energy required is suppose say 8 electron volts. Okay, when the height of the well is 8 electron volts, height of the potential. Okay, potential in quantum mechanics means potential energy only. Okay, right, now electrons inside it, some electrons have some 1000 electrons are like this. Some electrons have less energy, some electrons have more energy, some electrons have highest energy or maximum energy of say 5 electron volts. What is the minimum energy required to remove the electron from the surface of the metal? Minimum energy required means we should bring it out of 8. This to come out of this well, they should have minimum of 8 electron volts of energy. Some electrons are already having 5 electron volts of energy, means additionally if you just give about 3 electron volts, it is sufficient. The electrons which are having maximum energy by themselves inside the metal, they will come out taking this 3 electron volts of energy only. So if I send photons of energy 5 electron volts, what will happen? Right? They spend only 3 electron volts of energy to come out, and remaining 5 minus 3, the 2 electron volts will become the kinetic energy of the photoelectrons. Okay, but all electrons cannot come out by taking just 3 electron volts. Those electrons which are having maximum energy only can come out by taking 3 electron volts. What about remaining electrons? They need more energy to come out. Suppose say these electrons have, instead of 5, suppose say they have only 4 electron volts of energy, right? In order to come out, they should have 8. So when I send 5 electron volts photon, they take 4 electron volts out of it, right? So 5 minus 4, okay, the emitted electron will have only 1 electron volt energy, like this. Means the deeper the electrons inside the potential well, the more energy is required to bring them out. Okay, some electrons come out, take minimum energy and come. Some electrons need slightly more energy to come out. Means some electrons may take 3.1, okay, some electrons may take 3.2 electron volts, some may take 3.3 electron volts to come out, some may come out with minimum energy 3. Okay, some electrons will take only 3, some will take 3.1, 3.2, some will take 3.3, like this. Now I don't bother about all these electrons. I'll see what is the minimum energy required to bring one electron out. What is the minimum energy required to bring one electron out? 3 electron volts. I'll call that as my work function. Okay, so in solid state physics, in free electron theory of metals, we'll see this is surface energy ES, this is called Fermi energy EF, right? ES minus EF is equal to work function, we say. Whether if you give that energy in the form of light, it's photoelectric work function. If you give some other forms, some other work function. Okay, so phi is the minimum energy only. Okay, if I say 1.9 electron volts is the work function of a metal, okay, 5 minus 1.9, right, will be the kinetic energy of some electrons only, because some more electrons may not need may need more than 1.9. Some electrons may take 2 electron volts to come out. Okay, when they need 2 electron volts to come out, 5 minus 2, right, they'll come out to 3 electron volts only. Some electrons may take more energy to come out, okay, may spend 2.1, they come out with 2.9 electron volts only. Means in photoelectric effect, though I am sending photons of, okay, monochromatic photons, means same energy, 5 electron volts only, onto the same metal plate, okay, where work function is 1.9, the emitted photoelectrons will not exactly have 3.1 electron volts of energy. What about remaining? Some electrons only will have 3.1. What about remaining electrons? They'll have lesser than 3.1. Okay, because out from h nu, I'm taking out minimum energy required. So these electrons will have maximum kinetic energy. Very few electrons will have this maximum kinetic energy. Remaining electrons will have energy less than 3.1 electron volts. This is called distribution of kinetic energy of photoelectrons, or distribution of velocity of photoelectrons. Okay, though all photoelectrons are coming out from the same metal because of the same frequency light, their energy levels are different. Okay, right? Now how questions come, right? Questions will come, theoretical questions will come from this aspect also. When a monochromatic light is sent onto a metal plate, right, the photoelectrons, like that 4 options will be given. All photoelectrons will have same energy. The electrons can have any energy from 0 to infinity, any kinetic energy from 0 to infinity. They have one minimum energy and all possible energies above that minimum value. They have one maximum energy and all possible energies below that maximum value. Okay, which option is correct? They will have one maximum energy. Okay, they will have one maximum energy and all possible values below that maximum energy. Means this 3.1 becomes the most energetic electron. Other electrons may have 3, 2.9, 2.8 also, like that. Okay, so this is called distribution of kinetic energy of photoelectrons. All photoelectrons will not exactly have the same amount of energy. There is one specific maximum energy, K maximum, and remaining electrons will have energy less than that K maximum. Okay, now this is the Einstein's photoelectric equation. Now we can have different forms also, right? C equal to mu lambda, Okay, nu equal to c by lambda we can write. So the energy of each photon E equal to h nu. Nu equal to c by lambda also we can write. Nu equal to c by lambda also we can write. Okay, so the photoelectric equation will take different forms like this. Okay, the energy of each photon E equal to h nu equal to hc by lambda. Okay, when lambda is expressed in angstroms, okay, lambda is expressed in angstrom units, and I want the energy of the electron or photon or whatever it is not in joules or other forms but in units of electron volt, there is one straightforward conversion factor. What is that? Energy will get in electron volts, right? You can take this as 12,400 by lambda. Lambda should be in angstroms. When lambda is expressed in angstroms, 12,400 by lambda means I'll substitute the value of h, I'll substitute the value of c, simplify, I'll get the energy in joules here, meters per second, then I convert in meters into angstroms, I convert joule into electron volt, all that conversions I'll do. I'll get this ready-made formula. Okay. Right, when you take 12,400 by lambda, when lambda is expressed in angstroms, whatever result we get is the energy in electron volts directly. Okay, no other conversion factors are required. Okay, nowadays the wavelengths are being given in nanometers. Okay, if it is nanometers, 1 nanometer equal to 10 angstroms. Okay, so if the wavelength is given in nanometers, energy in electron volts E in electron volts is equal to 1240 by lambda. Now lambda should be nanometers. Okay, if lambda is given in angstroms, multiply with the 10 here, nanometers become what you call angstroms into 10 into 10, 12,400 by lambda in angstroms. If the wavelength is given in nanometers, 1240 by lambda in nanometers. Directly you will get the energy in electron volts, energy of the light photons in electron volts. Okay, right, remember this conversion factor, it becomes easy. So what is Einstein's photoelectric equation? Right, K maximum equal to h nu minus phi. We have written, what is this phi? Photoelectric work function corresponding to that minimum threshold frequency nu naught. So phi equal to h nu naught I can write. So h nu minus h nu naught. Okay, or h into K maximum equal to, right, h into nu minus nu naught. If the energy of the incident, if the frequency of incident photons is less than nu naught, nu minus nu naught will be negative. Kinetic energy can never be negative. So we say that it is impossible. Photoelectric effect cannot occur. Okay. From here also it can be understood why there is, what you call, the significance of threshold frequency. If the frequency of incident light is less than the threshold frequency, not even a single photoelectron will come out, irrespective of the intensity you use. Okay. That's why we use the word called when light of suitable wavelength. You cannot send light of any frequency and expect photoelectric effect to occur. Okay, the frequency of incident light should be more than the threshold frequency of that metal, or wavelength should be less than the threshold wavelength of that metal. Okay, right, now take nu as equal to c by lambda, nu naught as c by lambda naught. So it will be c also you can take common, hc into 1 by lambda minus 1 by lambda minus 1 by lambda naught it will be. Okay, now K maximum equal to, right, hc into 1 by lambda minus 1 by lambda naught. If you take LCM, lambda naught minus lambda by lambda naught, hc by lambda naught into, right, lambda naught minus lambda. Okay, if the wavelength of the incident light is, right, more than the threshold wavelength, okay, right, photoelectric effect cannot occur. K maximum will become negative. Means the lambda of the incident light should be less than the threshold wavelength or maximum wavelength. Nu naught is minimum frequency, lambda naught is maximum wavelength which can cause photoelectric emission. Okay, so in the exam sometimes some questions will come like this. Okay, so and so light of so and so, light photons of so and so energy are used on a metal plate with so and so work function, or its threshold wavelength is something like 7,000 angstroms. Which of the following sources can cause photoelectric emission? He will give you, he won't give you the wavelength of incident light, he will give you the energy of the incident light. Energy of the incident light is, suppose say 2.3 electron volts. Okay, photons energy is 2.3 electron volts. When these photons are sent onto a metal plate with threshold wavelength 7,000 angstroms, is photoelectric emission possible or not? What do you do? Right, and he has given energy now. Use this formula 12,400 by lambda. Okay, right? What is the wavelength corresponding to that 12,000? What you call that? 2.3 electron volts. So lambda equal to 12,400 by whatever energy has given. Take that here, energy of each photon. You will get that lambda. That will be the wavelength of the incident photons. If that wavelength is less than the 7,000, photoelectric emission occurs. If that wavelength is more than 7,000, photoelectric emission is not possible. Okay, right? So this is the what you call the photoelectric effect and its explanation with its what you call equations. Okay, now we'll draw some graphs in photoelectric effect. Right, the first graph is the intensity of light is taken on the y-axis, and I'll take what you call the potential on x-axis. This is zero potential. Okay, this is positive here, V is positive here, and V will be negative here. Okay, now this is our photoelectric tube, an evacuated glass chamber with a photosensitive metal plate. Okay, battery connected. There is one ammeter here to measure the amount of current. Okay, there is a positive plate here, anode. Okay, now initially I'll put V as equal to 0. I don't connect it to any battery, or potential is 0, say. Okay, when potential is 0, this plate is not negative, this plate is not positive, this plate is not negative. Okay, now I'll send 100 photons. Okay, 100 photons, each of energy, suppose say 5 electron volts. Work function of the metal is say 2.1 electron volts. So 5 minus 2.1, what is the maximum kinetic energy? 5 minus 2.1 is 2.9 electron volts. So maximum kinetic energy photoelectrons will have 2.0 electron volts. Remaining electrons will have slightly lesser energy than that. Lesser energy means, right, it can be 2.8 electron volts, or 2.7 electron volts, or 2.6 electron volts, like that. How many electrons will come? You have sent 100 photons, 100 electrons are coming. Now, this plate is not having any positive sign. There is no attraction of electrons towards that plate. Okay, so there is no rule that all the electrons which are coming should move straight towards this plate only. Some electrons may escape like this, some electrons may go like this, some electrons may go like this, some electrons may go like this. Okay, so we can't expect all 100 electrons to go and touch this metal plate and constitute current here. Okay, so because there is no attractive potential. Now, say even then some electrons will be moving straight towards that metal plate. Say out of 100, 60 electrons are moving straight towards the metal plate. So whatever current is flowing in the external circuit will be due to those 60 electrons only. Means even though the potential difference in the photoelectric tube is 0, current will not be 0. Okay, right? There will be some current because some electrons will come, right, and reach the plate. They constitute some current. Okay, right? Even when the potential difference in the photocell is 0, photoelectric current will not be 0. Remember. Okay, next one. Now what do? I'll increase the potential difference to 1 volt. Means this becomes positive, this becomes negative. It is 1 volt potential difference. Now what will happen? Right? Electrons, already some 60 electrons are reaching the plate without any attraction. When I make this one positive by 1 volt, what will happen? Electrons which are just missing the metal plate like this, and will get attracted towards this metal plate, such that number of electrons touching this metal plate will increase. Say now some 80 electrons will be able to reach the metal plate because of that attractive potential. Negatively charged electrons will get attracted towards positive plate. Okay, so what will happen when 80 electrons are flowing? Current will increase. Now I will still increase the potential from 1 volt to 2 volts, say. Okay, more attraction now, more number of electrons will get attracted towards the positive plate. They will be pulled towards the positive plate, such that number of electrons reaching the positive plate will increase. Photoelectric current also increases. Say now some 95 electrons will reach the plate, such that photoelectric current increases. Okay, I'll still increase the potential difference to 3 electron volts, or 2.9 electron volts, say, or 3 electron volts, whatever it is. Okay, what will happen? out of those 5 electrons, right, some electrons with maximum kinetic energy 2 electron volts, right, if they are going straight towards the plate or going like this or like this, they get attracted. But they are going in, suppose, same backward direction like this, right? Our 2 volts or 2.5 volts of attraction is not sufficient to pull the electron back towards it. But when I apply 2.9 or 3 electron volts, what will happen? Okay, right, even the electron which is going in some other direction also, right, because attractive potential is more than the maximum kinetic energy of photoelectrons, right, those electrons also will come and touch the plate, right, current becomes maximum. This time we can expect all 100 electrons to come and touch the plate, such that current becomes maximum current will be flowing like this. Current becomes maximum, right, and maximum current will flow like this. After that, even if you put 4 volts, 5 volts, 6 volts also, only 100 electrons are there. All 100 electrons have already reached the plate. Current has become saturated, we say. Means this is called saturation current. Okay, I call, or I1. Saturation current, I1. This is about the positive potential. What about negative potential? Now, instead of positive potential, say, now I'll apply negative potential. Means the tube is like this. I'll make this end positive and this end negative. Means now this not positive, it is not even zero, right? This one is having negative potential. And this is becoming positive. And electrons which are coming out have negative charge. Okay. Now what will happen? This negative potential will repel. The electrons will get repelled away from this negative charge. So they will not, earlier when there is no potential difference, how many electrons are reaching the plate? 60 electrons are reaching the plate. Okay. Now I am putting negative potential here. Negative potential will repel the electrons. So electrons which are touching the corners of the metal plate will get repelled away from this. So what will happen? Number of electrons, they get pushed out like this. Okay. So that number of electrons reaching the plate will become minimum, will become lesser. Now instead of 60, some 30 or 40 electrons only will come. So current in the photoelectric tube decreases. So even though I'm putting negative potential in the photo tube, current is not becoming zero, current is only decreasing, that's all. Now what do? This time I'll still decrease the potential. This time I'll still decrease the potential from -1 to -2 volts. This is means negative, more negative now. Okay, so what will happen? More forcefully electrons will get repelled away. Number of electrons reaching the plate still decreases. Photoelectric current also decreases. Okay, photoelectric current also decreases like this. Okay, but that -2 volts cannot stop an electron with maximum kinetic energy of say 2.9 electron volts from reaching the plate. Okay, right? Because negative -2 volts is not sufficient to push an electron which is coming with the 2.9 electron volts of energy. It is like something coming out with some energy of what you call 5 joules in one direction. You cannot apply a force, you cannot apply -1 joule of energy and stop it. Okay, in order to stop this one, you have to apply equal or more amount of force. Okay, sir. If you apply more amount of force, it moves in opposite direction. Some particle is coming out because of some force of 5 newtons. You want to stop that, means if you apply what you call 1 newton force in opposite direction, you cannot stop. Okay, minimum force you have to apply is 5 newtons in opposite direction. If you apply more force, it will start moving in backward direction. Okay, same is the case here also. These electrons are having 2.8, 2 electron volts of energy. Okay, some of them are moving straight towards this metal plate. Our negative potential of 2 volts cannot stop them. Okay. So they will overcome that negative potential, still reach the plate. Okay. Now what do? I'll increase the potential to -2.8 volts. Means this is becoming more negative now. This is becoming positive. Means electrons are getting attracted towards that plate of emission, and they are getting repelled away from the opposite plate here. Okay. Even when I put 2.8 also, current will not become zero. Why? Maybe some electrons with 2 electron volts of energy, they are coming straight towards the metal plate with 2.9. Our -2.8 cannot stop them. Okay, they will overcome that potential and still reach the plate, constituting some current. Okay, now what happens when I apply -2.9? Okay, when I apply -2.9 volts, already electrons with 2.8, 2.7, 2.6, they got stopped. Okay, Now electrons with maximum kinetic energy 2 electron volts, which are trying to move towards the plate, also will get stopped by this negative potential of minus 2.9. Means now the force is equal and opposite. Okay, such that these most energetic electron also cannot reach the plate. Then current becomes zero. Okay, so here the current is becoming zero like this. Okay, what potential difference? Minus 2.9. Okay. That is it minimum potential required to stop or a maximum potential required to stop? It is a minimum potential required to stop. There is no point of putting minus 3 volts or minus 4 volts. Not enough, not required. 2.9 sufficient. We are stopping the most energetic photoelectron from reaching the plate. Photoelectric current becomes zero. Okay, so it is the minimum negative potential required to stop the most energetic electron from reaching the positive plate. Okay, from reaching the plate is, or I can say it is the minimum negative potential required to make photoelectric current zero. That I'll call it a stopping potential Vs. That potential is called stopping potential. That potential is called stopping potential Vs, I say. So electron accelerated through V volts will have kinetic energy of EV, electron volts. So electron is accelerated by Vs electron volts, right? Vs volts. So its kinetic energy will be EVs. What is this EVs corresponding to? Now I said 2.9 volts. Okay, so what is the corresponding energy? 2.9 electron volts. Okay, right? Why is that 2.9 important? Because that energy is just equal and opposite to the maximum kinetic energy of the photoelectron. Means this EVs corresponds to this maximum kinetic energy, K maximum. Okay, that Vs stopping potential corresponds to maximum kinetic energy of photoelectron. Then only the most energetic photoelectron gets stopped. Photoelectric current becomes zero. So what is stopping potential? It is the minimum negative potential required to make photoelectric current zero. Okay, right? So this current is, this potential is Vs. It is inherently negative. I have to apply negative potential to stop the negatively charged electron. Okay, so this is the graph of intensity versus frequency graph. Intensity versus potential difference graph. Now everything same, right? Frequency of incident light is same, everything is same. Instead of 100 photons, I will send 200 photons. Means what? I am increasing the intensity. When I increase the intensity, right, the maximum kinetic energy of the electrons will remain same as 2.9 only. Only difference is what now? Instead of 100 electrons, 200 electrons will be coming. So what will happen? Instead of 60 electrons reaching the plate at V equal to 0, 120 electrons will reach the plate. So more photoelectric current will be there. Means only current will keep on increasing. Saturation current earlier was due to 100 electrons. Now saturation current is due to 200 electrons. But what about stopping potential? Maximum kinetic energy is still 2.9 electron volts only, isn't it? Therefore, the minimum negative potential required also will be minus 2.9 volts only. So, stopping potential remains same. Okay, so this is a graph of frequency constant, intensity increasing. Okay, so keeping the frequency of incident constant, when I keep on increasing the intensity, I will be getting graphs like this. Okay, this is one graph of intensity versus, right, potential difference in photoelectric effect. Okay, the next graph is, what do I do now? I'll keep intensity constant. I'll keep on increasing the frequency of incident light. Right, what type of graph we get? Right, we see now it is like this. Okay, the graph is now same, intensity versus potential difference. Only thing is, I'll keep the intensity constant, okay, and keep on changing the potential difference, changing the frequency of incident light. Okay, frequency is increasing, intensity is constant. Means I'll keep sending 100 photons only. So maximum of 100 electrons only can come. But initially, right, I'll send 5 electron volts photons. 5 electron volts photons. Work function is supposed say 2.9 electron volts. So maximum kinetic energy of photoelectrons will be 2.9 electron volts. Okay. So the graph will be almost the same here for this. Okay. We'll get the graph as before, like this. Okay. Right. Stopping potential Vs will be how much? Maximum kinetic energy is 2.9. So stopping potential will be minus 2.9 volts. Okay. This is saturation current because of 100 electrons. Okay. Now, instead of 5 electron volts photons, now I'll increase the frequency of incident light such that each photon's energy is 6 electron volts. So when 6 electron volts photons go and fall on the metal plate, right, what will be the maximum kinetic energy? 6 minus 2.1, it will be 3.9 electron volts now. Okay, but saturation current will remain as same before because only 100 electrons are there. Means the graph will be like this only, but this time the only difference is what? Stopping potential will be, right, minus 3.9. It's not 2.9 because minus 2.9 volts is not sufficient to stop the most energetic photoelectron with coming with 3.9 electron volts. In order to stop such an electron, right, I have to apply exactly minus 3.9. Okay, right, when I put minus 3.9 volts, then the most energetic photoelectron will get stopped, but saturation current will be same like this only. Okay, so this will now stopping potential will be this one. Means this is for lower frequency, this will be for higher frequency. Still I increase the frequency such that I'll send 7 electron volts photons. Now the maximum kinetic energy will be 4.9 electron volts. Okay, stopping potential will be minus 4.9. The graph will be like this. Okay, stopping potential remains same, but what you call, as you keep on increasing the frequency of incident light, stopping potential keeps on increasing. Nu3 greater than, Nu2 greater than, Nu1 we write. Okay, what is this graph? This graph is intensity is constant. Intensity is constant, right? Frequency is increasing. Frequency increasing. Okay, right? This is the second graph. The third graph is due to that equation. What is that? K maximum equal to, okay, K maximum equal to h nu minus phi. We'll draw a graph of frequency versus K maximum now. Okay, the third graph in photoelectric effect will be like this. Okay, on x-axis I'll take frequency, on y-axis I'll take maximum kinetic energy. I'll take maximum kinetic energy. Okay, now what is the shape of the graph? The kinetic energy K maximum equal to h nu minus phi. Phi is nothing but h nu naught. So h nu minus h nu naught. Till nu equal to nu naught, kinetic energy remains negative. Negative kinetic energy impossible. Photoelectric emission will not occur. Means up to nu equal to nu naught, there won't be any photoelectrons coming out. So when the frequency of incident light is more than nu naught, what will happen? This energy will be more than this energy. Kinetic energy also, as nu keeps on increasing, K maximum also increases, like a straight line graph like this. Okay, right? So the threshold frequency is nu naught. Here this one keeps on increasing with increasing frequency. This can be understood using this y equal to mx minus c form. This in which form means y equal to mx minus c form. Okay, right? The slope of the line is, this is nothing but K maximum equal to, right, h nu minus phi. Okay, y equal to mx plus c means it is a straight line with a positive y-intercept. Y equal to mx minus c means it's a straight line with a negative y-intercept like this. Negative y-intercept. So for negative y-intercept, what do we have here? Work function phi. Means in K maximum versus frequency graph, the negative y-intercept will give you the photoelectric work function. Okay, and what is m? M is slope of that straight line. Okay, instead of slope we have h here. Slope of this graph gives you the Planck's constant h. Okay, slope of this graph gives you the Planck's constant h. Now this is one more graph, K maximum versus frequency. Now we can draw, this is third one. Fourth graph is drawn like this. Now we have seen earlier K maximum corresponds to stopping potential Vs. So K maximum equal to EVS. So I can write photoelectric equation as EVS equal to h nu minus phi, or Vs, stopping potential Vs equal to h by E into nu minus phi by E. Okay, this is also in the form of y equal to mx minus c form. Means here also I'll get shape of the graph will remain same. Only thing is on y-axis we have stopping potential instead of maximum kinetic energy. Okay, on x-axis frequency only up to nu equal to nu naught, right? There won't be any photoelectric effect. Beyond nu naught only, photoelectric emission occurs as frequency keeps on increasing, right? Vs stopping potential also keeps on increasing, just like the straight line. Okay, now what is the slope of this line? Okay, for slope of this line we have h by E. Means this graph slope will give you h by E, and its negative y-intercept will give you phi by E. Okay, so as a negative y potential, okay, right, we have C as phi by E, and for what you call slope we have h by E. Okay, this is stopping potential versus frequency graph. Okay, now in the examination or sometimes in the interviews, which graph is suitable to find out Planck's constant? Okay, which graph is drawn in order to estimate Planck's constant? Question will be asked. So it looks obvious that it is this graph, because slope of this line directly gives you Planck's constant. So people think that this graph is preferably drawn in order to find out Planck's constant. No, but practically it is this graph, stopping potential versus frequency graph, is used to find Planck's constant. They'll draw this graph. Okay, they'll find out this line slope. Okay, equate it to h by E, multiply it with E, they'll get h. Why means we cannot measure the kinetic energy of photoelectrons directly. Okay, all that I can do in photo cell experiment is what? Okay, we can only measure the stopping potential like this. Okay, we can only measure the stopping potential. I'll make this one positive, this one negative. Okay, I'll send some frequency of light. Okay, and keep on increasing the negative potential. At what negative potential photoelectric current becomes 0, I'll see. Okay, that point is noted. Next, I'll send some other frequency. Instead of blue light, I'll send orange light or green light or yellow light, like that. I'll keep sending different wavelengths. Okay, and every time I'll change the potential difference, negative potential difference, still photocurrent becomes 0. This is experimentally easy. Okay, how can I find the kinetic energy of the photoelectrons directly? Directly we cannot find the kinetic energy, isn't it? So it is this graph which is drawn or which is used in experiments. Okay, we'll find out the slope, then multiply it with h, you will get Planck's constant. You find out the negative y-intercept. Okay, multiply it with E, you will get the work function of the metal used also. Okay, so this is another graph here. Now we can draw a graph of slightly different graph. Okay, not usually shown in many books also. We can draw photoelectric current versus frequency. Okay, photoelectric current versus frequency graph. This graph is little bit typical graph. Say nu up to nu equal to nu naught. Up to nu equal to nu naught, no photoelectric current. Okay, so I will be equal to 0. Beyond nu naught, what happens is, right, when you are increasing the frequency, current increases slightly, right, but only up to a point. After some point, again current starts decreasing like this. Okay, so if I draw with frequency, we'll get the graph like this. If I draw it with the wavelength, the graph will be like this. Frequency should be minimum frequency is threshold frequency, whereas in terms of wavelength it is maximum wavelength. So when I take the graph with lambda, up to lambda, for lambda equal to lambda naught, no photoelectric effect, nothing. Photoelectric effect starts from lambda less than lambda naught only. So as you are decreasing the lambda, right, frequency will keep on increasing. The graph will be like this. Again, when you are decreasing lambda, means you are increasing the frequency. Photoelectric current increases to some extent and then decreases further. Okay, this is in terms of frequency, this is in terms of wavelength. When frequency is intensity is, right, kept constant, 100 electrons only are going. Okay, but when you are increasing the frequency, initially up to some extent, right, current keeps on increasing. Current is increasing means is number of electrons increasing, or I equal to Q by T. Okay, is charge increasing? Electron number is same. Okay, charge is also same. How current is increasing? Time taken for the electrons to reach the positive plate may be decreasing. Current keeps on increasing. Okay, but then current should keep on increasing directly. After some time, even when the frequency is very high, why current is decreasing means some other effects will come into picture. See, we are talking about photoelectric effect means what? Light is coming and interacting with the electrons. It is nothing but interaction between radiation and material particle like electron. There are only three types of interactions possible between radiation and material particle. Okay, the first one is photoelectric effect, which is observed with visible light and UV light. Okay, if you increase the frequency to a higher value, to up to X-ray region, okay, the interaction between radiation and matter will be known as Compton effect. Okay, in Compton effect we use X-rays. Okay, X-rays have more energy, more frequency than visible and UV light. Okay, in the X-ray range, it is Compton effect which dominates. Probability for photoelectric effect decreases, probability for Compton effect keeps on increasing, current keeps on decreasing. Okay, still increase the frequency beyond X-ray region, go up to gamma region. Okay, millions of electron volts is the energy of the incident photon. Then the probability of Compton effect decreases, probability of the third interaction known as pair production will take place. Means these are the three ways in which radiation interacts with matter. One is photoelectric effect at lower frequencies, lower energies of the photons. At X-ray frequencies and X-ray energies, it is Compton effect which dominates. Probability for Compton effect will be maximum. Still increase the energy, still increase the frequency, the probability for pair production will be more than that of Compton effect or photoelectric effect. Okay, so many effects also, as the velocity of the electrons keeps on increasing to relativistic values, relativistic variation of mass factor will come into picture. 101 reasons are there for current to decrease, but this is the shape of the graph. As we go into, things will become more and more clear. Okay, so these are the different graphs we can draw in photoelectric effect. Now, note down as additional points. Okay, what all I have discussed, I have explained the effect, photoelectric effect, and the equations behind that. Okay, now we'll see some additional points here. What is that additional point? Quantum efficiency in this effect is only about 2%. That's all. Okay, quantum efficiency is only about 2%. Okay, as I'm explaining, I said, when I send 100 photons, 100 electrons will come, 200 photons, 200 electrons will come. That never happens actually. Only for explanation purposes, we say 100 photons, 100 electrons will come out. There is no guarantee or no rule that when an photon goes and hits the electron, the electron should come out. Okay, when 100 photons go and fall on 100 electrons, never 100 electrons will come. Okay, because there is no rule that electron should come out. Okay, the incident photon may not hit one electron, it may go and hit the lattice ion. Lattice ion will take that energy and it may re-emit that energy, or it may get heated up, something like that. When you focus light onto a metal plate for some time, metal plate slightly gets heated up. Okay, means lattice energy may increase, or that electron may absorb that energy and re-emit that photon. 101 things, or the electron may not feel like coming out. Okay, it may say no, not today, I won't come tomorrow. Okay, like that 101 things may happen. What practically happens is, when 100 photons go and fall, maximum of 2% means what? 2 electrons you can expect to come out. Okay, remaining some will be reflected, some will be re-emitted. 101 phenomena will happen inside the metal. When you send 100 photons, don't expect 100 electrons to come out. Okay, maximum of 2%. That's quantum efficiency is about 2%, 3% maximum. That's all. That's called quantum efficiency. Okay, so quantum efficiency in photoelectric effect is about 2 to 3%. That's all. Okay, that is one aspect. Second one, when I am sending this light photons onto a metal plate, large number of electrons are coming because electrons are large number. Free electrons are many in metal. So current, observable current is coming. If I send these light photons onto gas containing individual atoms, what will happen? These photons will go and hit the electrons in individual atoms. That electron will from individual atom will come out. Okay, when you take out an electron from a neutral atom, that atom gets ionized. Okay, because atoms are getting ionized because of the incident photons. That process is called photoionization. Okay, if I put one metal plate and one what you call one ammeter, etc., it is photoelectric current. Okay, if it happens with the gaseous atoms, it is known as photoionization, we say. Okay, and third point is, okay, in this effect, the energy of the incident photon is approximately equal to 5. Okay, work function of the metals will be around 1.9 to 2.1, 2.2. Most of the photosensitive metal plates work functions are around 1.9 electron volts to roughly around 2.4, 2.5 electron volts only. What are visible light photons energies? Visible light photons energies are from 1.78 electron volts to 3.1 electron volts. This corresponds to red color, this corresponds to violet color. Okay, so V, I, B, G, Y, O, R. Okay, red wavelengths, red photons have energy of around 1.7 electron volts. Violet, indigo, blue photons have energy about 3.1 electron volts. Okay, means when you are doing the experiment with visible light, the free energy of the incident photons is almost equal to the work function. This is the order of the work function only. Okay, so h nu is approximately equal to 5. When h nu is approximately equal to 5, the electron is considered as a bound electron. So this is a most important aspect in photoelectric effect and very popular among the questions, entrance examination like Central University or JAM, etc. Right? Photoelectric effect, the electron is considered as a free electron or a bound electron. The electron in photoelectric effect is considered as a bound electron. Okay, right? Though of course they are known as free electrons because they are roaming freely inside. As far as the incident photon is considered, okay, photon feels that the electron is not a free electron. Electron is a bound electron. Why? The binding energy of the electron is almost about the same as that of the photon's energy. Okay, so photon's energy is almost of course it should be more than 5 only, no doubt, for the electron to come out, but how much more? Slightly more, less than 1 electron volt difference only is there. So if you go and ask a photon with energy 3 electron volts and work function is supposed to 2.1 electron volts, right? For this photon, this electron with 2.1 electron volts of binding energy looks like a bound electron only. Okay, because it is eating away, right, almost its entire energy. Okay, so with respect to the energy of the incident photon, okay, right, the electron looks like bound electron only. Whereas if I send a photon with 10,000 electron volts, if I send a photon with 10,000 electron volts onto an electron which is bound to the atom with just 2.1 electron volts, say, a photon with a tremendous energy of 10,000 electron volts will not feel this binding energy at all. If you go and ask that photon, it says that electron is almost free. Okay, 2 electron volts is nothing for the 10,000 electron volts photon. So if you ask this photon, this electron is known as a free electron. If you ask a photon with 3 electron volts, same electron will look like a bound electron. So the electrons in photoelectric effect are considered as bound electrons. Okay, and till now what I am talking, I am saying that electrons will be there inside the metal. Our photons will go and hit the electron. Our photon gives the energy, electron comes out, we are saying. Okay, what about the incident photon? Okay, we have not talked about incident photon throughout my lecture of, right, photoelectric effect. We are talking about the electrons which have come out only, but what happened to the incident photon? Incident photon disappears after the interaction, means it gives its entire energy, loses its entire energy and disappears. Okay, after the interaction, incident photon does not exist. Okay, that entire photon means a quantum of energy only. That entire energy is given to the electron. Electron only comes out, means in photoelectric effect, right, only electron appears after the interaction. Okay, what happened to incident photon? Got disappeared. Okay, right? Why? Means a bound electron can absorb the energy, all the energy of the incident photon. Remember, in photoelectric, these are the points which come in MS entrances. Okay, right? Photoelectric effect, the electron is considered as a bound electron. Why? The energy of the incident photon, h nu, is almost of the order of the work function. Okay, so the incident photon feels that the electron is a bound electron. Okay, a bound electron can absorb all the energy of the incident photon. Bound electron can absorb all the energy of the incident photon. Okay, that's why incident photon gives all its energy to the electron and disappears after the interaction. When I go to our next topic, okay, where I'll be using X-ray photons, okay, an X-ray photon's energy is very much greater than the binding energy of the electron. There we write h nu very much greater than 5. Okay, for such a photon, the energy, right, binding energy of the electron is so small, this photon feels that electron is a free electron only. Just like, see, for me, if somebody gives me a chalk piece, normal chalk piece what we see, I can simply break that. The chalk piece is a bound one, it has some binding energy, but compared to my energy, the binding energy of chalk piece is so small, not only me, even 5 years old small kid also can break the chalk piece. But can I break the pen into 2 pieces? No, it's not possible with me. Why? Its binding energy is more than my energy. Okay, so if somebody asks me, is it a hard pen or a weak pen, means I'll say it is a hard pen for me, because I may be able to break it, but I have to use my entire energy to break this pen. Okay, breaking this pen is not as easy as breaking the chalk piece. Okay, but if you go to Bahubali or Ballal Deva and ask him to break this, right, they can break the pen, nothing. So if you ask Bahubali, this pen is like a chalk piece only. Okay, whereas the same pen is very hard for me. Okay, because his energy is 1,000 times more than my energy. For him, the binding energy of this pen is nothing. He will say it is as easy as chalk piece only for him. Okay, so pen is same. Okay, whether it is bound or free depends on the energy of the incident photon. Energy of the incident photon in photoelectric effect is almost the same energy as this one's binding energy. So photon feels that electron is a bound electron. Okay, whereas in Compton effect, I am using X-ray photons with 10,000, 50,000 electron volts of energy. Binding energy of this electron is nothing compared to the energy of the incident photon. So if you ask that photon says this electron is a free electron only. Okay, so that is the case of Compton effect. That is our next chapter. Okay, next topic. Now here in photoelectric effect, the electron is a bound electron. A bound electron can absorb all the energy of the incident photon. That's why the incident photon disappears after the interaction. Okay, in the next topic, Compton effect. Okay, h nu very much greater than phi. So the electron is a free electron. A free electron cannot absorb all the energy of the incident photon. Remember, that's why in Compton effect, what will happen? Right, the incident photon goes and hits the electron. Electron cannot absorb all the energy of the incident photon. It takes only a part of the energy of the incident photon and gets recoiled. Okay, incident photon still remains. Incident photon gets scattered. So in Compton effect, right, scattered photon also will be there, electron also will be there. In photoelectric effect, there is no scattered photon. The incident photon got disappeared, got lost. Only electron is there. So in the examination, they won't even specify whether it is photoelectric effect or Compton effect. They simply say a photon interacts with a bound electron. Okay, after the interaction, what happens? Electron disappears, photon disappears, both appear, both disappear. They say bound electron means it is photoelectric effect. Okay, in photoelectric effect, only what you call electron will come out, photon disappears. Instead, the question comes, and photon interacts with a free electron after the interaction. When a photon is interacting with a free electron, that is Compton effect. In Compton effect, both the electron will be there and photon also will be there. A photon gets scattered with somewhat lesser energy. Electron will recoil with that extra energy what it has gained. Okay, so Compton effect or photoelectric effect also will not be mentioned clearly. If it is a bound electron phenomenon, photoelectric effect. If it is a free electron phenomenon, Compton effect. Okay. So this is about the photoelectric effect. Okay, the next topic will be, and we'll see some problems also in the next video. One or two problems which have come. 2020 IIT JAM also one simple question has come in photoelectric effect. 1 mark question. Just by looking at the problem, you can just answer it. Okay, very straightforward, easy question has come. But the problem is some students made mistake even that also because they have neglected photoelectric effect. Okay, they think that preparing for IIT JAM or CSR or GATE means they are solving very big problems, complicated problems like that. No, be thorough with your concepts, be thorough with fundamentals. Okay, for the examiner there is nothing like a tough question or an easy question. Okay, there is nothing like an important topic or a not so important topic. All topics are important for the examiner. All questions are equal, will have equal weightage there. He doesn't feel that this is easy, that is hard. No. Okay, and he never thinks that this topic is what you call important, the topic is not important. All topics are important from teacher's point of view. Okay, so you cannot neglect any topic, right? In the syllabus you have to go through all the topics only. Okay, right? We'll continue in the next video. Thank you.